Al finalizar el año 2020 y con el contexto mundial que vivimos, nos damos cuenta de que hablar de digitalización no es una proyección del futuro, sino un hecho que ya se encuentra revolucionando la realidad tal como la conocemos. Pero ¿cuál es el punto de partida si deseamos transformar nuestra empresa en una organización digital de cara a los mercados de energía? La respuesta la tendremos a continuación con nuestra conferencia magistral, la digitalización de la industria energética y los datos como clave del éxito. Conozcamos a nuestra ponente. Nuestra prominente conferencista expone las bases del tema que nos reúne a lo largo de estos 3 días. Iniciamos la conferencia. Bienvenida, Cornelia.
Good afternoon, ladies and gentlemen. Let me briefly introduce myself. My name is Cornelia Krome and I'm from FH Aachen. First, I would like to present my research background. I'm a research assistant at one of the biggest universities of applied sciences in Germany. We are one of the research strongest ones, and our main competences are the future areas energy, mobility, and life sciences. The FH Aachen is located in a region of former open cast mines. Together with various research institutions and companies, we are shaping the digitalization and transformation of the energy industry in the region. Today, I'm here to give you a brief breakdown of the digitization and digitalization of the energy industry. My talk is divided into 2 parts. I start with terminology and introduce digitization and digitalization in general. Then I will give you multiple use cases of digital technologies in the energy industry and will explain 3 of them in more detail. But before I start, I would like to mention a few examples of digital technologies that come to my mind. When I think of digital technologies in my environment, I have smart homes and the Internet of Things in my mind. Objects in my environment get an ID. They can communicate and interact with each other. All elements are connected. Hence, applications can get automated without human interventions. Additionally, I think of digitized industries and processes. Through connected machines and systems, entire industrial processes can be automated. Consequently, production processes are more efficient and cheaper. As I am a mathematician, I use data to make predictions and analyze them. And I need those data. For example, data of stock prices. But when we save them, it is possible to get another view of processes. With advanced analytics, fluctuations can be predicted and assets can be managed. And in the energy industry, I think of smart metering. They are one way to digitize and subsequently analyze the data. As electricity meters, they are part of the smart grid, the intelligent electricity network. But with the increasing digitalization of our environment, there are also new security aspects to consider. A secure grid is necessary for us all. However, regardless where we look, digital technologies are everywhere. They accompany our everyday life and simplify many things. So I've mentioned digitization and digitalization several times, but what is the difference between these 2 terms? First of all, digitization. It is a process of changing from analog to digital form, also known as the digital enablement. Said another way, digitization takes an analog process and changes it to a digital form without any different in-kind changes to the process itself. So long story short, digitization is the process of converting analog material to a digital form. Thereby, data, processes, and actions are getting digital. For example, keeping the digital version of a photo instead of the paper one is digitization. And digitalization is the use of those digital technologies to change a business model and provide new revenue and value-producing opportunities. It is the process of moving to a digital business. So digitalization is the usage of digital technologies and the adoption of a business model. When we watch Netflix, for example, instead of getting those videos we are watching from a movie rental stores, we make use of digitalization. So as we can see, digitization is necessary for digitalization. Without data, digital business processes are impossible. But about which amount of data are we talking in the context of the energy industry? We're talking about a great amount of data, the so-called big data. Big data is high volume, high velocity, and high variety information assets that demand cost-effective, innovative forms of information processing that enable enhanced insight, decision-making, and process automation. The Digital Readiness of Central America's Energy Sector report concludes that the digital core technology areas are just the mentioned Internet of Things, advanced analytics, and the blockchain technology. Through the Internet of Things, smart physical objects get connected so that they can interact with each other. With advanced analytics, predictions can be made. Additionally, they provide safety and manage assets. And finally, blockchains can be used to encrypt, store, and distribute data. In the following, I would like to name some use cases in the energy industry of digitized data. By connecting the physical objects of a company or a household, an intelligent energy consumption is possible. Therefore, the Internet of Things is necessary. When all objects are connected, a grid can be remotely monitored and managed. Intelligent software solutions can display important aspects in particular and visualize the current key figures. This allows problems to be found and solved quickly. A special application of the Internet of Things are virtual power plants, which I will discuss later in more detail. And with advanced analytics, charging stations for electric vehicles can be controlled. Maybe they are part of the virtual power plant. Through machine learning algorithms, consumptions can be optimized and predictions of, for example, renewable energy output can be made. The blockchain technology is still young in the energy industry. Nevertheless, applications have been researched in various projects. One conceivable possibility is the trading of electricity. So come to the first use case, the virtual power plant. In a virtual power plant, several decentralized power producing units are conglomerated. Those medium-scale units are such as wind farms and solar parks. Additionally, flexible consumers or storage systems can be included, such as households or groups of households and companies. A central control unit connects all single units. Thereby, all units stay still independent. They control themselves on their own. A virtual power plant shall relieve the load on a grid. The combined production and consumption of the network can be traded on the energy exchange market. So small consumers and producers work together as one bigger player. The integration in a VPP facilitates the prediction, optimization, and trading of all partners as one single power plant. Fluctuations in the generation of renewables can be balanced by ramping up and down power generation and power consumption of the other controllable units. One participant may be a company or a household with a charging station for e-cars in front of their house. Therefore, let me introduce you a charging point management system. So imagine you have an e-car and a corresponding charging station in front of your house. Most of the time, the car is not connected with the charging station because you use your car to go to work or somewhere else. Therefore, it would be possible to sell the free capacity to other users. Different fares would be available: fast charging, cheap charging over a long period of time, and so on. With an intelligent charging station management tool, it is possible to control the station. Therefore, the OCPP transmission protocol enables the management of the station. It gives information about the connected car, about which model is linked or how fast can be loaded. Now we can expand the single charging station and think of those many parking spaces in a city. Here we have all those single parking lots, and every supermarket has parking lots on their own. Think about all the big malls and their capacities. When we sum them up to all the parking lots to one big parking space, we can see the arrival and departure rates and observe all of them. They are different and depend on the daytime, day of the week, and seasonal effects, as we can see on those two graphs. There are 2 arrival peaks per day, except on Saturday. So we have Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday with only 1 peak. Combined with the departure rates of a day, one can say that many people come in the morning and stay for a whole working day. Afternoon is the next peak of the arrivals. So in the morning, all the people who are working in the city come and park their car, and in the afternoon, maybe people who can shop. Comparing the days to each other, one can see that on Wednesday and Fridays, the afternoon peak isn't strongly marked. So here it is very small, and on Fridays too. In Germany, medical practitioners are usually closed at this time. So less people maybe need to park their car to get in the city because they wanted to a doctor. People who come in the afternoon only stay for a short time. Some of them go to the doctor, others might go shopping, but all leave in the evening. So if those parking spaces are connected to the grid, there are many possibilities. Same as for single households, special rates can be offered. For example, a quick load option for less than 1 hour parking is possible. Customers who stay longer, for example, a whole working day, pay less because they offer flexibilities. Many more options are conceivable. And those many connected stations provide new flexibilities. Electricity shortages and surpluses can be compensated by different charging strategies. During a shortage, the loading process of a long parker can be interrupted, and for this purpose, they can be loaded with increased capacity in the case of surpluses. Therefore, the charging station management system knows the constant performance limit and can change it to a dynamic performance limit. Additionally, dependent on those arrival and departure rates we've known from the mall parking space, load profiles can be simulated and forecasted. Based on the results, capacities can be bought cheaper a day ahead. I'd like to expand on one more example. Therefore, let me elaborate on clustering time series. I'd like to show you the day-ahead prices in 2018 in Germany. The energy price relies on many aspects and has a very special behavior. Scarcity and abundance have high impacts. Additionally, the price is related to performance. Supply and demand have to coincide at every point in time at every place in Germany. So shortages cannot be equalized by profusion at another place or time. As you can see, the day-ahead price is as volatile as stocks. Every day has to be analyzed separately, and holidays vary greatly from normal weekdays. Here you can see one exemplary week. The mean price within a week is mostly constant. A systematic decrease at weekends can be observed. So Fridays, Saturdays, and Sundays, the price is lower. There is a high demand fluctuation that is originated by business hours at a daily level or changing climate conditions. For example, an early rising of the sun or the working days at the 8 hours of a day, mornings and evenings when all get home. There are big differences between winter and summer. In winter, there's a peak in the evening when all people get home and need some light. And in summer, the energy around noon is more expensive. Taking holidays, we could see a great difference to normal weekdays. Therefore, holidays need to be analyzed separately. We implemented an algorithm to analyze generic time series and cluster the results so potential action strategies for virtual power plants can be derived. For the algorithm, the day-ahead prices of the electricity market for 2018 are used. Each day gets transformed to a time series of 24 observations. The time series are the input data for the algorithm. For each time series, Multiple models are fitted. The parameters of each model serve as features in the time series of the time series. Then similarity functions are applied to the featured data, which results in distance matrix and according groups of models, the so-called clusters. First of all, I would like to show you how we analyze time series and how we can fit time series models to our day-ahead prices. By analyzing time series, the focus of the analysis is the dependence between adjacent observations. A very important feature of time series is stationarity. The joint probability function of a stationary model does not change when the stochastic process is shifted in time. So it is important to distinguish between stationary and non-stationary time series. If a stationary time series is available, the deterministic trend can be estimated. Together with an analysis of the residuals, a forecast can be made. Therefore, autoregressive and moving average models are used. In a non-stationary time series, there is a varying fluctuation. The data have no seasonal component and the residual process is non-stationary. With a variance stabilizing transformation and building the difference of the process, the behavior of a non-stationary time series can be obtained. Let's have a look at those two types. First of all, the stationary time series. An autoregressive moving average process is a combination of autoregressive and moving average models. The left part here in this equation represents the current value of a process as a finite linear combination of previous values, t minus p. As x is regressed by previous values of itself, the process is called autoregressive. On the right side, we can see a moving average part. This represents x linearly dependent on a finite number of previous random noise. They consider the error of the process. With a mix of both models, more flexibility is achieved. They are called autoregressive moving average models of order p and q. If q is equal to 0, the ARMA model is equivalent to an autoregressive model of order p, where only past values of the time series itself are taken into account. The same applies vice versa. If p is equal to 0, we have a moving average model, where only past noise is masked. Non-stationary time series are different. To analyze those, autoregressive integrated moving average models are used. Non-stationary time series can be transformed so that the new series is stationary. The Box-Cox transformation stabilizes the variance of the process so that stationarity is obtained. Afterwards, an ARIMA model can be adapted. In particular, if there are d unit roots, the ARIMA model of parameters p, d, and q is indicated by this equation. The functions phi and theta represent the autoregressive and moving average part of the model. P is the number of lagged autoregressive terms, D is the number of non-seasonal differences needed for stationarity, and Q is the number of lagged forecast errors in the prediction equation. An autoregressive model with P equals 1 can be expressed similar to an ARIMA model. So B is just a backshift operator and simulates the last part of X. An ARIMA 010 model represents just a random walk. For example, stock prices are mostly a random walk. Generally spoken, time series that are adapted with a model with d equals 0 have constant mean over time. Models with d equals 1 include a linear increase or decrease as trend in the process. Now we fit the models to the day-ahead prices. They are converted into 365 time series with 24 nodes each. Before a model can be adapted, stationarity must be checked. If necessary, the time series gets transformed with a Box-Cox transformation. One example for a non-stationary time series are the values of December 23rd. The variance differs throughout the day. The variance stabilization transformation is applied to the time series to bring the non-normal dependent variables into normal shape. Since the logarithm As applied to the data, the new values differ greatly from the original ones in magnitude. Nevertheless, the transformation is necessary for model adaptation, but the values are not relevant for their ARIMA parameters. Those values would be important for prediction, in which case the inverse Box-Cox transformation should be applied. In this case, the maximum value of the time series for the December 23rd lies under 70 euros and above 10 euros. When we transform this time series, the time series takes values between about 40 euros and 230 euros. But as I've said, those values aren't of any usage for the transformation or for the models to adapt those. They are just for prediction values necessary. After a transformation, multiple ARIMA models are fitted with the F function auto ARIMA. The function chooses the model order D by unit root test in the beginning. Afterwards, different models are fitted to the given time series. Whether a model is appropriate or not, pertaining the randomness of the time series, can be tested with the long box test. Therefore, a fitted model is satisfactory if the model residuals are uncorrelated and resemble white noise. As D represents the differences used to get stationarity, only P and Q need to be checked for a good fit. The archaic information criterion, or short AIC, is used as a prime criterion for model selection. All models with an infinite AIC are eliminated and a validation with the Young box test is performed. Models whose AIC is greater than the median of all AICs are discarded. On average, the median AIC of the different models per time series is greater than 52% of all AICs. After the time series are fitted, we can get our featured data. So we have a set of M proper models. Here, M can differ for each day because of the elimination process described. The restriction of the models to all those whose AIC is smaller than the median corresponds to a confidence interval with a flexible confidence level for each time series. The model parameters as well as the AIC for each model are saved in vectors P, Q, and AIC. They form the features of our time series. After the features are found, we need to get some similarity functions to calculate a distance matrix and get the clusters. The first approach is to use the AIC as similarity function to select the best model. It is known that all reasonably small AIC values should be considered as potentially appropriate and evaluated according to their simplicity. Hence, one might rather want to select a less complex model over the one with the lowest AIC to gain more stability. That is why we saved all models with a low AIC and not just the lowest one. The ARIMA orders P and Q indicate the complexity of the model. In order to reduce the model complexity, another similarity function is contemplated, namely the MAIC. First, a map is defined to order a vector x. It's just the bar x. Based on this map, the MAIC is defined by a linear combination of the normalized versions of AIC and the model complexity. As a result of the elimination process, the AIC of all models tend to be very similar. Additionally, the AIC involves the logarithm of the likelihood function. Thus, the parameters P and Q might be undervalued because of their low valence. Only models with low AIC are included in the analysis because we eliminated all models with an AIC higher than the median. So the attention is already focused on good approximations. Therefore, we choose an alpha equals to 0.9. With alpha greater than 0.7, the results were stable, and 0.99 was chosen to put the complexity of the model in foreground, but still measure the AIC in the rating. Based on those similarity functions, we can build our distance matrix. After all time series have been analyzed, the data sets are scrutinized for clusters. The different time series are categorized by ARIMA parameter D, here in front. An algorithm is performed which selects the amount of clusters, so that every time series can be adapted to at least one model. After all clusters are determined, every time series is mapped to a cluster by a similarity function. Thereby, those clusters shown here are used. Therefore, we get the clusters with best possible compactness and separateness properties. While there are 5 or 6 clusters for d equals 0 and 1, there exists only one cluster for d equals 2. So all time series that were clustered with a d equals 2 ARIMA model are in the cluster 1, 2, 0. But these were only 5 time series for the whole year. Based on the distance matrix, we can build our clusters. Therefore, every time series has to be mapped into a cluster. So any fixed day k is classified as ARIMA, PL, DK, and QL, where L is the minimum of the argument AIC. We take fixed day k, and D is just k and not L, because D is exactly the same for all models of one time series. Only P and Q differ. By taking the MAIC as similarity functions, we get the star parameters. The resulting models are saved as triplets, so 2 vectors of the assigned models are obtained, model K and model K star. The modification of the MAIC allows to trade small increases in the AIC for the selection of less complex models. Let's start the analysis and show the clusters. First of all, the labeled clusters gets their names by the PDQs, and for further analysis, I've displayed the holidays in Germany of 2018. You can see the New Year's Day, Easter, or Christmas. Additionally, the school holidays were put on this frame because we have Christmas, Easter, summer, autumn, and the Christmas holidays in the end. For visualization purposes, the time series are displayed according to the weekday. Each graph shows one specific weekday. Here you can see an exemplary Thursday. So the weekday is on top of it, and an extra plot shows the adapted models for those German public holidays. Those groupings are made for presentation and have no are just the optical analysis. There is no a priori knowledge for the algorithm. Each time series is represented by a dot in the plot. Their coordinate is a triplet of their cluster, for example 200, and the date when the time series occurs. A tick on the main y-axis marks the first day of each month. So the 1st of January, 1st of February, 1st of March, and so on. As only 5 days are adapted with d equals 2, the cluster is not shown for clarity reasons. It is interesting that those were only winter days. The vertical lines here between the clusters split the plot into models with d equals 0 on the left side and d equals 1 on the right side. The color of each item represents the corresponding cluster, just for visual analysis. With the help of this graph, I would like to explain how the time series were clustered for 2018 with the AIC. Overall, 12 clusters were discovered. 11 are represented here. 4 main clusters can be found. The ARIMA 200, the blue ones, ARIMA 110, the yellow ones, ARIMA 011, the dark red ones, and ARIMA 012, the purple ones. For each day, the distribution of the clusters differ, but some similarities can be observed. For Mondays and Sundays, many time series are adapted by models with d equals 1, so that there are many points in the left part of the plots. If d equals 0, then the time series are mostly modeled with the ARIMA 200, So on the left side, we mostly have those blue dots. This is more likely in our summer months. So in the winter, we have many d=1 models, and those models with d=0 are more likely during the summer break, so from Easter to autumn. For Tuesdays through Saturdays, most time series are adapted with ARIMA 200 models, the blue ones. Tuesdays are evenly divided between ARIMA 200 and models with d=1. So there are as much models on the left part of the plot as on the right part of the plot. On Wednesdays, ARIMA 200 is very dominant as well. There are many blue dots in the plot. But during summer days, some others are adapted by d=1 models. Most or harder, the half of them of the days. On Thursdays, ARIMA 110 models are very likely to. So the yellow ones attract attentions. For Fridays, it appears that they are very similar to the Tuesdays. We have models in the ARIMA 200 and nearly the same amount of plots with d=0 are on the right side with d=1. Except for Saturdays in summer months, many time series are adapted with d=1 models. As I've said before, d=1 models have a trend in it. So they have increasing or decreasing values from the morning till the evening. This appears to be more likely in the summer months. For public holidays, so the last plot of this model, we model with d=1 are very dominant in winter. So there's a trend in winter. During summer, all time series are adapted by models with d=0. Here from Easter to the autumn months. The second clustering uses the MAIC similarity functions where the model complexity receives greater attention. And we can see this in this plot as well. There are only 3 groups that attract attention: ARIMA 200, ARIMA 110, and ARIMA 011. They are simpler than those of the AIC clustering, and overall 337 days are modeled with one of these. Half of the year is modeled with a d=0 model, and the other half with d=1. For this clustering, the distributions differ for each day too, but there are some main differences. For all day, simpler models are chosen more often. So the blue ones, the yellow ones, and the dark red ones are just most of them. And these are the simplest models that were adjusted by the algorithm. In the clustering, Fridays attract attention, this part here in the bottom. A shift from models with d=1 at the beginning of the year to models with d=0 in the end can be observed. So in the lower part, we have more models with d=1, and till winter, there's a shift, and more models are modeled with ARIMA 200. An overall comparison between both clusterings shows that when using the AIC similarity functions, there's a lot of variation between clusters, and complex models are chosen more often. The modified version uses simple models instead. We can see this on this plot. This plot shows just in 3 parts the d=0 models, d=1 models, and the d=2 models, and the same for the MAIC. The bars represent the numbers of time series that were modeled by such a model, splitted by the weekday. We can see that there are just less models used with the MAIC, just mostly 200, 110, and 011. And there's more differences with the AIC. An example for a shift are for d=0 and clustering with the AIC, we have 136 days in cluster 200 here, just on the left. 19 in 300, the next one. 16 in 200, the last one of the d=0 part. 9 in 100. And with the MAIC, as similarity functions, we have the shift here. There are only 2 days are displaced from somewhere else in 101, a very simple model. One comes from the 300 and one from 400 models. These are very complex, though there are strong simplifications. Additionally, 35 days are shifted into group 200, which is much easier than the others. An analogous behavior can be seen for d equals 1. All in all, it has a high concentration on clusters 200, 110, and 011. 92% of all days of a year are grouped in those clusters. We can see the shift I've explained here in this plot as well. An arrow symbolizes a change from one model with AIC to another model with MAIC. The dot represents no change. So when the arrows goes from right to left, we have a much simpler model than with the MAIC than with the AIC. When we are using now our domain-specific knowledge, the presented results can be used to formulate statements that can be of a significant use for specifying a business strategy. Many Saturdays are adjusted with an ARIMA 200 model. Thus, the next hour is predicted from the previous 2 hours. The error terms are not considered in the model. It is noticeable that also the ARIMA 200 model is frequently used through the whole year. In winter months, however, a trend is found in the data. So models with d equals 0 are used and would be suggested for prediction purposes. To review the algorithm, the day-ahead prices for 2016 and 2017 are analyzed as well. For both years, similar observations can be made. As seen before, clustering with AIC results in more groups with complex models than with MAIC. This can be seen, for example, in 2016 with d equals 1. We have much complex models where there's a shift from those complex models to a more simple model. The distribution of the clusters per day is similar to 2018. Most Saturdays are adjusted with the ARIMA 200, and on Sundays those models are used as well, but a trend is often found in the data. As in 2018, the days mapped with d equals 2 are only during winter. The analysis of aggregated generation of hydropump storages demonstrates that the algorithm is not only applicable for day-ahead processes. The daily generation can be analyzed with the introduced algorithm. Since this behavior differs from that of day-ahead prices, other models are chosen for approximation. There are 3 main models: the ARIMA 300, dark blue here, ARIMA 110, it's a light green variant, ARIMA 111, it's a red with the red dots, and we can display 264 days, so over 70% of a year with those models. In contrast to day-ahead prices, models with d equals 0 are much less frequently selected than models with d equals 1. So there is more often a trend in the data. Almost no Saturday or Sunday is modeled with a d equals 0 model here in the bottom. And so almost all days are adjusted with d equals 1 models. All in all, we have seen the time series can be clustered based on their model parameters. Since not only using the AIC as similarity function is used, but also the model complexities considered by the MAIC, simpler models are increasingly preferred. To briefly describe possible applications of the procedure, I would like to return to virtual power plants. To develop optimization strategies for multivariate problems are an important part of the operation of a VPP. Good demand-supply management not only requires current price data, generation data is also included in the analysis. For example, if a VPP knows the price trend of electricity and can react to forecasted price signals in the short or medium term because of small units, the electricity costs can be reduced. Thus, the value of the additional or less consumed electricity can be estimated. This enables to inform customers about potential savings, in addition to the applications presented. This is intended to apply the described workflow to the energy management data of clients of a VPP. For example, imagine you're a bakery, or you own a bakery. Bakeries are very important in Germany because we love bread. And if you work in a bakery, your most working hours are in the early mornings. Therefore, the power consumption for ovens, etc. is especially high in the morning hours. As we have seen before, power prices are cheaper in the morning than at other daytimes. But why shall you pay an average price for the whole day? If you are included in a VPP, there are possibilities to make a special fare for the bakery and from the energy provider so that you pay less for the early morning hours. Concert halls apply maybe the same. They use the energy mostly in the evening. Maybe there a special fare is possible too. Based on the results of a cluster analysis, potential action strategies for energy provider can be derived. A use case may be the clustering of clients. Historical consumption patterns might be found which can be used to cluster different clients. Further analysis may get a better quotation for each customer so that they have to pay less for energy and the provider can predict the consumption more precisely. Based on the large amounts of data provided by digitization, new opportunities arise. Digital business processes can be implemented to work more efficiently and cost effectively. The data can also be used to interconnect grids flexible and better to manage the electricity. The need of storage and reserve capacity increases because of the growth of variable electricity generation. They are necessary to manage the imbalances between demand and supply. The energy supply gets fragmented through the spread of prosumers. Additionally, renewable energy is becoming financially competitive. To combat climate change, it is determined to reduce the emission of CO2. Furthermore, good quality of air includes the reduction of particulate matter and nitrogen oxides. The population growth and off-grid users will lead to an increase of demand for electricity. By analyzing the consumer's behavior, new business strategies may arise. In summary, data is the key to success. Without data, digitalization is not possible. And that brings me to the end of my presentation. Thank you for your attention.